Hi everyone, welcome to my presentation on doing BPF programming with C++. This is the third part of my presentation series called A Gentle Guide to BPF Programming. So today we are going to have a pretty short video because we've already covered the basics in previous videos. Specifically, the video that you should watch to kind of go over a lot of the important things that we're doing is the Python video that I recorded last weekend. And it should be easy to find. I'll link to it somewhere around here or in the description. So what we're going to do is we're going to grab the necessary tools to be able to use BPF with C++. We're going to make sure that we've got the correct documentation up and available to us, and then we're just going to start coding it. So we need the reference guide for BCC, and we also need the C++ API. So in order to get them, do a Google search for BCC BPF, click on your first link. And for the reference guide, you just scroll down to where you see reference guide and you click on that. And for the API, the way that you get that is you go into the source directory, then go into the CC directory, the API directory, and the file that we want to look at is bpf.h. Another way to get that bpf.h file is on your hard drive at user include bcc bpf.h. Now, before you are able to see that file, you're going to have to install the necessary tools. So those necessary tools are here on this command line, and I will put this command line in the description. They are libelf-dev, libbpfcc-dev, bpfcc-tools, and clang is a nice to have, although it's not completely necessary. So I am going to copy and paste that into my window here. And I've already installed them all, so that's why it said it didn't need to do anything there, but we've got everything that we need once we've entered that command, and we can start coding things. Before that, let's also get that bpf.h file inside of our text editor here. So here it is, and you will see that it's the same thing that you get if you look at it on the GitHub repository. So let's start coding. First thing that we need is let's just include iostream so that we can print things out. And then we want to include bcc bpf.h. And that is this file. Let's do an int main void. And we will just return a 0 here so that we've got something to start compiling. So we'll go into code, cbpf, and call this tt.cpp. And I've already got a makefile set up for us. It's probably good to go through this makefile. So the important things here are the libs that we need to link against. So here's, you need lbcc, libbcc, you need libbcc-bpf, and you also need to link against libelf. So I am using clang for my compiler, but you don't necessarily need to do that. And this app equals test is just a nice way that I use to kind of make my makefile all nice and easy to use. So let's make with app equals tt. And we will run tt and it will not do anything because it doesn't do anything. So let's start coding up some BPF programs. So the way that you do your BPF C code is you have a raw string, so an std string, and we're going to call this BPF source. We're going to set it as a raw string, and we are simply going to have a function called mmap, because that's what we're going to hook in this this exercise. It will take a parameter of a void pointer to a context, and we are not going to be using that context in this video, so don't worry about it. But that is what we're going to be kind of setting here, because mmap does take a it's actually a pointer to the registry, but don't worry about that right now. And in this, we are going to do a BPF trace print k and say hello world. And we will return a 0. Now, to get that BPF code injected into the kernel, what we do here is we have an eBPF object called BPF. We will do a bpf.init with that BPF source, and it's good to go to our header file here and see what's going on. So we are doing we're calling the constructor for this BPF object. We're not giving it any parameters here, and then we are doing the init. So init, and it should take the program as its that's that BPF program, the BPF source, as its inputs, and it's got default parameters for the C flags if you want to compile it up with a bunch of kind of W error and things like that if you want. And I don't use the USTD, so maybe I'll look into that in a future video, but for right now we're just going to ignore that. So the next thing that we want to do is actually find out what mmap is in what the actual name of mmap is as the system call. So a function that BPF gives you is get syscall fn name. So we're going to use that auto, we're going to call it syscall, and it's going to be the bpf.get underscore syscall underscore fn name, and we're going to get the mmap system call, and let's just print that out. So the first thing that we do is on kind of easy prototype code, I like to just get the using namespace std in here, because I don't like namespace std, because I don't like typing std all the time in front of my couts. So let's do the syscall we are hooking is called syscall. And let's compile this up again and run it. Interesting. Okay, and let's keep going here. So we want to attach a trace probe to BPF. So bpf.attach trace probe. Actually, we're doing a K probe here, not a trace point. We're going to do attach a K probe, and attach K probe, and the function, the kernel function that we are hooking is this syscall. And the probe function is this mmap. So let's actually call this mmap-fn. And it actually returns a return code here that we should check against. So if rc.code is not equal to 0, then error the rc.message now, and let's return a 1. But if everything's good, then we'll continue on. And we will just do a sleep here for 10 seconds, allowing the prints from this trace print k to go into the tracing trace pipe area where our trace print k's go. So we've got that there, and let's compile it up one more time. mmap-fn, and we need to put this as a string. Now this should give us an error because we can't inject BPF functions as a normal user. We have to be a super user. All right, so we're hooking it now, and sorry for the meanness of Pop! OS's tiling functions there, but as you can see, the hello world code is being called inside of the trace pipe. And let's just do that one more time. But let's open up a tab. Oh, new tabs don't seem to do anything here. Oh, okay. How about fresh tab there? Nope. Okay. How about we just do an LL? Oh, it's because we're not running here. Okay, so now we're running. We'll do an LL, and we should see messages inside of Hello World. All right, so our program is running. We can see our print inside of the trace pipe, but we're not really doing anything right now. So I have another program already coded up, which does a lot of the work that we usually want to do with BPF code. And the function that I've created is called test more. So let me go through this test more function, this test more program. So what we've got is our BPF source code, and in our BPF source code, I'm creating a perf event, and the perf event is the communication ring buffer that we can write to in our kernel and read from in our user space program. We're using a structure called data t, and in that data t, we've got a PID that will take the PID of the program, which is calling mmap, and the com of the name of the program calling mmap. So one of the tricky parts here about using these structures is that you can see I've got both the structure inside of the BPF source, and I've got the structure inside of my C++ code. This is a bit of an annoying thing that you have to do because what we're doing here is after we get the information to fill out the structure, we're basically writing into that ring buffer that structure as a series of bytes. And in our user space program, we want to grab those bytes off and use them as the structure that we know from what we've written. So it's a bit of an annoying thing that you have to do with C++ BPF programming, but the easiest way to do this is to simply write the structure once and then copy and paste it into your, so We'll just copy and paste it into our BPF C code. So what we do is we declare that structure. We get the PID TGID, and we're only going to get the TGID here because we're shifting over 32 bits just to get the TGID. We're then getting the name of the program calling mmap by this BPF get current com. And just for your reference, all of this information is in the reference guide. So let's do a search for BPF get current com. And here it is. And it tells you about how to do things with it. And the get PID TGID is here as well, and it tells you all about that. We've gone over this stuff in the previous video, so I don't want to go too deep into them. We've got that hello world program, that hello world function, just printing out to the trace area. And we are doing the perf submit, just like this is all just exactly like how we did it inside of our Python code in the previous video. So the important C++ code is that this is what we had in our previous tt.cpp. But what we're doing here is we're opening up that event perf buffer as we declared it here. So we're testing to make sure that we opened it correctly. And then we're just doing a forever loop, hopefully a forever loop, polling that perf buffer. So when we open the perf buffer, we give the name of the buffer that we're opening, and we give a handler to a callback function, which will take the information and do things with it. In that handler function, let's take a look at the API for that, the open perf buffer function inside of the bpf.h. So it takes the string to the buffer, and it takes this callback function. Now they've typedefed the callback function that they want, and they're calling it a perf reader raw CB, a perf reader raw callback. So where do you get that information? How do I know that takes this specific signature? Well, I did a grep for perf reader raw CB, and I did a grep for it inside of user include, and I see that in bcc libbpf.h, I see that typedef for the perf reader raw callback, and it is a void, and it takes as its signature a raw callback to a callback cookie. It takes a void pointer to the data, or the raw, and the size of the data. So I've got that coded up. So what I'm doing here is I am static casting the raw data into a data t pointer as defined here. And then I am simply spitting out the PID is dpid, and the com is dcom. So let's give this a compile and run. So let me first make clean app tt, and I don't have, let's make clean app. Let's test. So we're going to compile up app equals test more. And then we are going to run test more. And what we're doing is k-probing the mmap function. So you can see that we're getting a lot of output here because things are happening. So let's just do an LL in another window here. And you can see that ls is calling mmap quite a lot. Quite a bit more than we would expect from such a simple program, but that's what happens. And you can see the mmaps occurring from all the other applications that I'm running on my system. So we do a a new tab inside of Firefox here, and we see a whole bunch of things running. I've got Nautilus running, doing a whole bunch of mmaps behind the scenes. My OBS is calling mmap quite a lot. Mmap is a function which is mmap is a system call which is used quite a lot. So it's as simple as that to get yourself going with C++ BPF programming. I hope you have learned something, and thank you very much for watching.